Part 2, let's make a tree from a letter distribution. So first, let's understand the problem. Look at this picture here. We have letters A, B, C, D, E, F. And we have a distribution where 45% of our letters are A's and 13% are B's, 12 C's, 5 F's, 9, and so on. 9 E's, 16 D's. Okay? So this happily adds up to 100. And the way that Huffman encoding works is you start out just thinking of each of the letters as their own tree. Of course, they're going to eventually be leaves. And the frequencies are the important label here. So F's are labeled with 5 and E's with 9. And then you put them all into a heap or a priority queue, and you pull out the two smallest ones. And if you look at these weights, 45, 12, 13, 5, 9, and 16, the two smallest ones are 5 and 9. You pull that out and you combine them into one letter, if you would, the letter EF in this case. Okay. Well, if F has 5 and E occurs 9 out of 100 times, combined they occur the sum, 14. And you put this tree back into the heap. Now we have 45, 12, 13, 14, and 16. The two smallest now turn out to be 12 and 13. Combine them into 25 and put that back in the heap. The two smallest now are 14 and 16, combined into 30. Then the two smallest are 25 and 30, combined to 55. And finally, the two smallest are 45 and 55, combined to 100. So you keep doing this until you only have one value left in the heap, and then that's your answer. Okay? So we're ready to write a little bit of code. We want to make a tree. We want to make this tree out of a list of letter frequencies, where letter frequencies look like this. I have 45 A's, I have 13 B's, 12 C's, 16 D's, 9 E's, and 5 F's. It's exactly this problem right here. Okay? And then after we've made our tree, calling make tree, we want to get a tree that equals this tree. Let's see that this does that. This is a tree who his value at the root is 100, and we're going to have a label be all the letters represented by that node. Okay, 100, A, B, C, D, E, F, all the letters. The left-hand side, the left child, is just one node, weight 45 and A. The right-hand side is a weight of 55, and all the letters below here are B, C, D, E, and F. The left child of the 55 is that 25. The left child is right there. There's the 25. Its left child is 12. Its right child is 13, and so on. And you can convince yourself, hopefully, that this tree matches that tree. Pause the video and convince yourself if you must. Okay? Great. So how do we do this? Here we go. So make tree letter frequencies. The first thing is we have to put all of these into a heap, which we discussed in our lecture. A heap is a data structure that takes a bunch of values and gives you back the smallest one that remains so far in the heap. So if I can say import heap q, I'm just going to show you down here. I'll have my heap be an empty list, and I'll say heap q dot heap push into my heap. I want to push the value 5 and the value 17 and the value 2 and the value 8. Now if I pop out of my heap, I'll get the smallest value that's in there, which would be the 2. Okay? If I do it again, I'll get the 5. I can push another value in. Right now, by the way, what's in there right now? The 8 and the 17. If I put a 4 in there, and I put a 16 in there, and now I pop, I'll pull out the 4, then I'll pull out the 8, and the 16, and finally the 17. If I try to heap pop again, I crash. Great, we're going to use that here. My heap will initially be an empty list. I first have to put all the letter values and letter frequencies in the heap. For each letter frequency in my letter frequencies, okay, that means for each one of these things, I need to heap q dot heap push into the heap. I need to put that letter frequency. But in fact, if you think about it, when that letter frequency is a tree all by itself, it's actually in a list like this. So I want to put that letter frequency in a list so that it matches our tree data structure. It's a tree with one node, and that node happens to just be that one letter. Great, I have now added them all to the heap. Now, so long as the length of my heap is greater than 1, I need to pop out the left child and the right child. So child 0 is heap queued at heap pop heap. I pull out the left child, and I pull out, zoops, the right child. I now have the 2 children. Now each child has a label to start with, okay? And that label is this. It's this tuple of the weight, or the frequency, and the label. So my frequency of child 0 and my label of child 0 is the 0th element. Remember, child 0 itself is a tree, the way we're representing it, and the first element in that tree is, in fact, the label, then the children. I'll do the same for the right side. You might need to pause and think about this a little bit. Great. Now I have the left child and the right child. My combined frequency for this node is just like that 12 plus that 13, that 12 plus that 13. The combined label for this node is going to be the label on the left side plus the label on the right side. But the thing is, that might be F, E, and D. So this is EFD. And if I did EF plus D, well, let's do it this way. EF plus D, I get EFD. But if I sort that, I get DEF, and then I can join that back, and I get the string DEF. Great, so my label is the join of the sorted of the combining of those 2 labels. Hopefully that made sense to you. My node, finally, is what? Well, it's this combined frequency with this combined label with my left child and my right child. And all I do is push that back into the heap. So I pulled out the left child, I pulled out the right child, I grabbed their frequencies and labels, 12C and 13B, I combined them into a combined frequency of 25 and a combined label of BC, and then I created a node of all of that combined tree and stuck that combined tree back into my heap. I keep doing that till I'm done. When there's only one left, heap of 0, so do this way, return heap.pop. Pop out that last element, and that will be your answer. And look, it worked. So this function actually takes in the letter frequencies, which look like this, and produce this tree, which in our representation looks like that. And again, here's your code. Cool.